So my name is Erik Österlund, and I'm one of the GC guys in the Oracle Java Platform Group. And today I'm here to present about the evolution of colored pointers in ZGC. I'll talk a little bit about how colored pointers used to look, how they look today, and some of the adjustments we're making for the future. Before we talk about colored pointers, it's useful to first revise the anatomy of a normal pointer. So let's do that first. So on a 64-bit platform like x86-64, the pointer is it's a 64-bit integer, and it describes the address of a byte. And with virtual addressing, these bits are sort of split between page offset bits and virtual page indices. This is because you have 4 kilobyte pages. Let's assume that's 4 kilobytes for now. And then the page offset bits describes a 12-bit offset into a 4 kilobyte page. The other virtual page index bits are mapped through a memory management unit to look up the physical page that's being accessed. And among these virtual page indices, not all the bits are actually useful. With a canonical x86-64 address, the high order 16 bits are sort of pointless sign extension bits that have to exactly replicate the highest order useful bits. And the convention is that the kernel is allowed to use negative addresses, but user space uses positive addresses. Because of that, there's actually 17 bits that are not very useful. And the rest can be used to address memory user space, which gives you about 128 terabytes of addressability. These virtual page indices, they're composed of multiple levels of paging. So if you have 4 levels of paging, which is quite common, there's a tree inside of the kernel to look up which physical page to use for a particular address. And these trees correspond to the 4 different levels of paging. And at the top level, have a global directory, root node, and there are 9 bits to tell which child in this node to go to. And that takes us to page upper directory node, and another 9 bits gives us the next child to page middle directory node, and so on and so forth to the leaf level page table entries. And that's where we get a mapping to actual physical page. And you can also use large pages. If you use large pages, you essentially remove the leaf level page table entries, and instead they go directly from the page middle directory straight to a 2 megabyte large page. This makes it easier for the memory management user, memory management unit, because it caches common paths in this tree with translate look-aside buffers, and it requires less entries when you use large pages. Recently, there's been a push also to use 5-level paging. We can churn in yet another level here with another 9 bits, and it gives us a few less colors in the high order bits that are 0. So this is sort of the anatomy of a normal pointer, which takes us to the more interesting thing, which is colored pointers, or as I call it here, pointer chromodynamics. The idea with colored pointers is to embed metadata inside of pointers. So it represents an address, but also a bunch of extra metadata bits. And this has been a very crucial thing in the design of ZGC. And using this, we can encode state machines in the pointers themselves. And when a state transition happens, we go from one color to another color, can perform some kind of GC action that is useful for managing concurrency. So this is what a normal object graph might look like. You have a thread with a root, points at some object, and it transitively can reach other objects. And with color pointers, we can encode properties of the objects by encoding these properties inside of the pointers. But we can do more than that. We can also encode properties of the edges themselves, which can be orthogonal to the properties of the objects. And this sort of leads us to how there are really two different types of color pointers, called these persistent colors and transient colors. Persistent colors are colors that stick around after a load. You read the reference and you still have the colors. Whereas transient colors are a bit more slippery, and as we load the reference, the colors disappear and are instead restored later on. So let's talk a bit more about persistent colors. So with persistent colors, since the bits stay around after a load, they become part of the object address. And because they're part of the object address, you can only really encode properties of the object. Because if you start exposing different bit patterns pointing to the same object, you might get into a situation where you need object identity barriers, because you have objects that look like they are almost the same object, plus minus some bits. And you don't really want to have object identity barriers. These color pointers should also be, if you have persistent colors, dereferenceable. And in order for them to be dereferenceable, you probably don't want to use low order bits, because the low order bits, well, they will change which byte we're addressing, and that's no good. And you'd have to do some kind of masking as well. You don't want to do masking, software masking with your colors, because that has a significant performance overhead. So instead, what you do is you encode the color bits in high order bits and try to inject yourself into this virtual addressing machinery that I was talking about. There are different ways of doing that. You can have multi-map memory. You can use hardware address masking in the CPU itself. And you can also try to partition the address space and encode color properties using addresses. Looking at multi-map memory might look something like this. That we have some high order bits used for colors, and for every normal address, we are creating multiple mappings to the same physical memory. And through these multiple mappings, we can have dereferenceable addresses pointing to the same memory with different color bits. Looking at hardware address masking, I think Spark was the first to have virtual address masking, where you could have a configurable number of high-order bytes that the hardware will just ignore when you dereference a pointer. And then AR64 has a sort of similar top byte ignore feature that allows you to ignore the high-order byte. On Intel machines nowadays, you get Intel's linear address masking. The number of bits you get there sort of depends a bit on the level of paging that you're configured to use. With 4-level paging, you have 15 bits, and with 5-level paging, there are 6 bits you can use that the hardware will just ignore when you dereference. AMD has a similar feature called upper address ignore, and it uses 1 more bit. I guess we're less afraid of the high order bits changing the sign. This takes us into the colors of the past, what we used to do in particular talking about the non-generational version of ZGC. What we did then is we used multi-map memory, and we mapped the same virtual memory 3 times, corresponding to our 3 colors we had, with 2 marking colors and 1 color for remapping. The reason there are 2 colors for marking, call them here mark even and mark odd. It allowed us to recognize which object had been mark the current cycle versus the previous cycle, and which one is the current versus the last one would alternate between odd and even for every GC cycle. The main idea is when we change the globally recognized good color, which is one of these three, it renders all pointers in the heap bad. And when you have a bad pointer and you read it, we get to perform a color transition that can perform a GC action, which is either marking or relocation. Right. And looking at the color pointers, the layout looks something like this. We have 3 high order bits there at the very top, corresponding to our 3 multi-mapped colors. This yields itself for pretty efficient load barriers. An x86-64E looks something like this, where there's a conditional branch that checks if the loaded reference has the right color. If it didn't, well, we're going to have to go into the runtime and perform a color transition, which also requires triggering some GC actions such as marking and relocation. Let's take an example. In this example, we're running in the interface with the remapped color is a good color, and we have a bunch of edges in our object graph here, and they're all looking good. They have the expected good color. Now, if we change the globally recognized good color to marked even red color, that renders all of the pointers in the heap bad. And as the application thread starts loading these references, it will have to mark the objects that it's reading and update the pointers, perform the color transition. But it might be that the application isn't really accessing all of these objects, so the GC threads will help out and perform marking, make sure that the entire object graph is marked through. Then we change the phrase again and select a new good color, remap bits. It's a good color. And as we start accessing objects, we shade them the corresponding good color. And if we change the mark E odd phase here, perform some extra loads, you'll see that at this point, we have all 3 colors represented here in the object graph. We have marked odd, marked even, we have remapped colors. But after the GC marks through, we purge out all the old colors and we end up with only 1 single color. And this is why we need only 2 marking colors, because we occasionally flush out all the bad colors and make sure that there's a single color in all the edges. So looking at a bit more detail, what things look like when we try to reclaim memory. You can have a heap region looking something like this. We have some pointers in here for live objects, and around these live objects there's a bunch of garbage. What we want to do here really is we want to move these 4 live objects out of there so we can reclaim the memory of the entire heap region. Now, if we try accessing object 1 during the relocation phase, this will trigger evacuation of that object because we recognize, oh, there's a bad color here. Let's see what we need to do. We need to move the object and perform this color transition to the new good color. And after that, we can access it with no trouble. As we access object 2, the same thing happens. We evacuate the object and everything works fine. And the GC can help with this work too. It can move objects. So objects 3 and 4 can be moved by the GC so that we can reclaim the entire heap region. Now the GC here is not messing around with the pointers. It's only moving the objects. All the pointer fix-up is lazily done by the mutator. Right. And now at this point we can reclaim this memory, even though there's still pointers pointing in to this memory we freed. Normally that you wouldn't be doing that. You don't free memory that you have references to. But with colored pointers, we can distinguish that these pointers into this free memory, they're stale pointers, and we will lazily remap them if they're accessed. After it's reclaimed, we can allocate new objects in here, fill it up with a whole bunch of new objects, and we can create a new edge here to the object number 9. And now at that same location where object 9 was allocated, we had references to that exact same address before. That was actually object number 3. So if we try to dereference pointer here to object number 3 through the same pointer, we'll recognize that, oh, that had the wrong color, and go into the runtime and figure out what's happened here. The object has moved. This was actually object number 3, even though it had the same address as object 9. So we call this instant memory reclamation. It's a feature that allows us to reclaim memory just after evacuating objects from a heap region, even though things are still referring to the objects in there. And it's pretty cool. Normally you'll have to wait until remapping or something later on. And because this feature, that not only do we have less floating garbage, but the memory that we're freeing can also be used to facilitate more memory reclamation. So this allows us to move all the objects around without the need for there to be any reserved memory up front, which you usually need. And this is a pretty cool heap efficiency optimization. Now, the one thing that we don't have because of that is compressed OOPS. Compressed OOPS is kind of incompatible with the idea of caller pointers. If we have so many caller bits, we can't really compress the pointers. Compressed OOPS is also a memory efficiency optimization. It's a bit more straightforward in the sense that you compress the memory than you use less memory. And I think this works really well in a stop the world collector, because in a stop the world collector, you finish remapping before you release a save point. And yeah, that allows you to just get the benefit of freeing or of compressing the objects. But with a concurrent garbage collector, you start exposing a world where we have multiple different pointers to the same object. We can't really free the memory until remapping. And it comes at a cost then to keep memory around until remapping has finished, which means you can't really use, or you need to reserve a memory up front for moving objects around. So compressed pointers, pretty cool, and small heaps, and can be used for most of the world situations, but non-obvious costs when you have a concurrent GC. Whereas instance reclamation still works pretty well in small heaps, but scales more better on larger heaps. And in my very unbiased opinion, it's also a cooler way of saving memory. So these 3 colors weren't really enough for non-generational ZGC. As we started looking at concurrent reference processing, it turned out that finalizers was very fun to deal with. So in order to implement phantom reference versus weak reference semantics correctly, the GC needs to distinguish whether an object was reachable from strong rooks or only from a finalizer. And in order to deal with this, we had to add more colors to the pointer to represent whether an object being marked through a finalizer or through a strong reference, which was a pain. But fortunately, this bit was always a bad bit because you never exposed it to the user. You won't always mark it strongly. So this was in fact our first transient color bit because it was just removed by the load barriers. And so these 4 colors are the ones we ended up with non-generational ZGC, 3 persistent color bits and 1 transient color bit, which was, we didn't have to multi-map. But that's not where we are now. Today we have a generational garbage collector, and it's way more complicated. With the generational garbage collector, we have 2 different drivers of our GC cycles. We have minor collections that trigger young generation collections. And we have major collections that trigger both young generation collections and old generation collections. And this required a more involved state machine for our color pointers. In fact, we ended up with 12 color bits. And as you can imagine, with multi-map memory, you start running into problems there, that the TLBs get very sad when you have so many combinations of the same memory. And there's also a bunch of kernel bookkeeping, and it just doesn't really scale that well to this many color bits. Another thing that we struggle with non-generational ZGC was something I call RSS inflation, because RSS counts the multi-map memory for each mapping. And people complain that our RSS looks like it's 3 times higher than it should be. And we keep saying that maybe we should look at the PSS value instead, because it better reflects how much physical memory you're using. But in the end, it turns out that everyone is looking at RSS. The containers look at it, and the C group memory controllers themselves are looking at RSS. So at some point, I think we sort of had to accept that everyone is sort of doing the wrong thing. And so we have to change something. And to deal with that, created what I call colorless routes, which was a way of getting transient colors, and like way more transient colors. And this allowed us to get rid of the RSS inflation, because as we load a pointer, we would remove all the colors, so we don't need to multi-map memory at all, as it turns out. And yeah, so the loads would remove the colors, and stores would recreate the color that it should have had it been tracked. The idea then is that we still have the idea that color transitions trigger some kind of GC action. The load barriers are concerned with figuring out the first load of a GC phase. And the store barriers are concerned with detecting the first store of a GC phase. The loads will trigger relocation. The stores deal with marking and remember set maintenance. Looking at the layout of our color pointers, they look a bit more shiny now with more colors. Low order bits are being used instead of high order bits. And that's because, well, we're removing them anyway. So starting with remapping bits, these bits encode somehow whether an object might have moved, either due to the young generation or the old generation, or maybe both. Then we have marking bits that say something about how an object has been marked, by which generation, and with which strength. And last, we have remember set bits that are used to figure out if a reference is part of a remember set or not. And for those of you who don't recall what a remember set is, if you perform a store here, creating an edge from object 4 to object 2, then we have a so-called old to young pointer, a pointer from the old generation to the young generation. And we need some kind of bookkeeping here to recognize that when we're collecting the young generation, object 2 is still reachable. If we remove the last reference in the young generation to this object, it's only reachable through object 4. So from the young generation collections perspective, you can look at the remember set here and see that, oh yeah, we need to trace through object 2 and keep that at light as well. Otherwise, we'll crash, which is bad. To manage all these colors, we have a sort of increasing level of goodness scheme, where starting at the lowest level, we have a property called load good. If a color pointer is load good, it means that the remappings are correct, which means the address is stable. Might be all sorts of problems otherwise, but at least the address is stable. The next level of goodness is called mark good. it means that the address is stable, and on top of that, we also know that this edge has been marked, so we don't need to mark it again. And the ultimate best level of good is called store good. And this is what stores produce. And that means all the color pointer bits here have the good shade. Means it's also tracked in the remember set. One interesting thing here, at least I think is interesting, is that with generational ZGC, not only are we tracking properties of the objects, such as whether it's been marked or whether the object has moved, things like that, we're also tracking properties of the edges themselves. And the remember set, it's really a property of the reference fields, not of the object. It says whether the field has been added to the remember set or not. And as we talked about previously, you can't really model that with persistent color bits without requiring some kind of object identity barriers. So yeah, this was one reason as well why we changed to use transient colors, because we had some colors that really needed to be transient, and we had no colors that needed to be persistent. So we just made all of them transient. Let's look at some barriers. So on the left side here, we have the load barriers, the way they use in non-generational ZGC. 2 instructions, checking, now do we have the right color here? If not, we need to perform a color transition and do some form of action. The right-hand side, we have generational ZGC. Here we also have 2 instructions, but we're doing a lot more. We're checking if it's the right color, if it's null, does it need some kind of color transition? But we're also removing the colors, but still we're not using more instructions. And this turns out that this was pretty tricky to get right, and that it took over 10 different iterations of barrier models until we ended up here. And it's worth mentioning that the blue stuff is immediates that are concurrently modified in order to get this right with cross-modifying code. There's a corresponding store barrier that plays with this. It checks if the previous value has the correct color or not. If it doesn't, well, then we'll have a color transition. We need to do something in a snowpath. And after that, it colors the pointer and stores it. Uses 4 instructions is okay, especially for a store barrier. A bit more forgiving. Let's look at the possible states we have in these color bits. I talked about how we had odd and even marking in the non-generational ZGC. It's a sort of similar thing in generational ZGC, that most of these colors come in pairs, that they're 2 bits with either value 1, 0, or 0, 1, meaning some action happened in the even or in the odd phase. There are also some 1, 1 and 0, 0, meaning that, and the action did in fact not happen. All makes sense until we get to the bottom with the remap bits. There we have 4 bits and only 1, 1. And yeah, what does that all mean? So we want to have this even and odd stuff that we can reason about. Turns out that if you take these remap bits, look at the position of the 1, you can represent this as an index of the bit being set. And if we convert that to binary, we have a 2-digit binary number here, where there is a low order bit and a high order bit. Well, we can map the low order bits to the young generation and the high order bits to the old generation. And that way we can map this to even and odd states for the 2 generations, which is pretty cool in my opinion. It all makes sense. Okay, so let's look back at the colored pointers. This is what they look like. Beautiful. Now, if we set the remap bit to 1000, remember that when we remove the colors was a shift instruction, but the immediate of the shift instruction depends on the phase of the GC, and it depends on what the remap bit index is. We want to remove all the colors, right? So we have to remove everything up until that 1, which makes sense when the color is 1000. But if it's 0100, notice that the address bits are shifted 1 space, and we start having a intersection between the address bits and the color bits. So the 0 is both an address bit and a color bit. It seems fine. And we can continue this with exactly 3 zeros, because that's what the object's alignment allows us to do. With 8-byte alignment of objects, the low order 3 bits are always 0. And therefore, there's no ambiguity whether these zeros belong to the address or the color, because both interpretations are correct. And yeah, this is what allowed us to make efficient load barriers in generational ZGC using color pointers. And yeah, it's pretty cool. With generational ZGC, you can have not 2 different bit patterns of pointers with the same address refer to different objects, but up to 3. So you can have a colored pointer pointing at an old object that moved, a colored pointer pointing at a young object that moved, and a new object, all sharing the same address, but referring to 3 completely different objects. And it allows us to get rid of floating garbage, and we don't need memory to move objects and things like that. Also makes generation sizing quite fluid and allows it to automatically tune generation boundaries very easily. And most importantly, efficient barriers. So that's where we are at today, but let's talk also a little bit about the future. One of the exciting things we are looking towards in the future is separating private versus shared objects, so we can more efficiently collect private objects, thread local GC call. But we still want the ability to fall back, of course, on the generational GC we have today, and that optimization doesn't pay off. So we know we have 12 transient colors today, and it allows us to do some interesting things. But one of the things we can't do with these colored roots is to encode object properties. We've gotten really good at encoding edge properties, but not object properties. And the thing is, the separation between private and shared objects is more fine-grained. For different objects, they're private, and for some of them, they're shared. So for this, we can't really use transient colors. We need persistent colors. What this implies is that we're really going to need a combination of transient and persistent colors. But we don't want to go back to the RSS inflation problems we have with multi-map memory. We'll get to that. But yeah, we basically want some kind of private bit here in the pointer that tells us about whether the object is private or shared. And in our colored pointers, it might look something like this in the high order bits. So one of the things we've worked on recently to allow this is unintuitively a new mechanism for how we manage free memory in the heap. We used to have a mechanism called a heap region cache that cached the regions that have been freed. This was a little bit problematic in terms of virtual address space fragmentation. So a lot of work has been done to revamp this and create a new way of managing this memory, where ranges of freed memory is cached in something like a map heap cache instead. And comparing how fragmentation might have looked like before, a heap might have looked something like this, but with this new mechanism, it might look a bit more like this, with a lot less fragmentation. One of the things we had to deal with in this transition is how to manage memory when you have multiple NUMA nodes. So in this case, let's say we have 4 different NUMA nodes. We have more explicit tracking now of where memory is mapped. And we call this heap partitions. Here we have 4 different partitions of the memory corresponding to the different NUMA nodes, and it allows us to allocate memory close to your current NUMA node. Makes sense? But these heap partitions can also be used to implement persistent colors in a way that doesn't really run into the RSS inflation issues that we have with multi-map memory, because there's a one-to-one mapping to memory still. And it's just that we partitioned the heap in such a way that certain bits in the pointers are fixed to a certain bit. One limitation of this is that you can't just change the color without moving the object as well. But that's no limitation in this scheme. So concretely, it might look a bit more like this, that the high order part of the address space has the private bit set to 1, but within that space, we can still have different NUMA nodes in other heap partitions. And similarly, we have a shared space underneath that, which can also have different NUMA nodes or NUMA partitions inside of it. And this is pretty cool and allows us to implement this private bit without using multi-mapped memory. And then we might also start using the 4 unused fix in the lower order bits because they looked a bit dull. So a summary. With non-generational ZGC, we started with 3 persistent color bits, had to add on 1 transient bit for reference processing, but suffered from RSS inflation. With generational ZGC, we got a much more powerful algorithm. We got rid of the RSS inflation issues and moved over to use 12 transient bits instead. And looking forward, we're overhauling the algorithm again, and seems like we're ending up with 16 transient color bits and 1 persistent color bit, but with an even more powerful algorithm. Thank you. All right, we have time for questions, I think.
So when you talk about the private local or private memory,
Yep.
do you depend on escape analysis, or is that discovered by GC? So
Yeah.
you discovered by GC that it's local.
Yeah.
So then until the GC discovers that, it's treated as global.
Yes, right, exactly.
And then you relocate it to the private partition once you discover that it's local.
Right.
And it can become global at some later time, then you have to move it back?
Yes, eventually.
Okay.
The main design goal is to make sure things don't get worse than what we have today, because what we have is pretty good. So instead of one of these schemes where, oh no, something escaped, let's do something horribly expensive, we're instead trying to apply less of the new cool optimization and wait things out until we can reapply it again.
Okay, thanks.
Let me try this one. Is there a limit on the number of threads that can possess private heaps? Is it limited to the number of NUMA partitions?
No, there's no limitation.
Because each one knows they can all point into one private partition, but they each know who their set is?
Oh, I see what you're saying. So yeah, it's way more fine-grained than that. The private heaps are sort of like discontiguous and linked together and can be small, allocated inside of heap regions that are located in the private part of the heap. But the small heaps for the threads are way more fine-grained.
I'll be embarrassed if I'm the only one who doesn't know. What's a NUMA partition?
Sorry?
What's a NUMA partition?
What it is, or it must be, if you have, for example, different CPU sockets, it might be that accessing memory from the other sockets than your current one is way more expensive. So in order to deal with that, you try to put your memory close to your own CPU so you don't have to go through the overhead of poking around at another CPU's memory.
Okay, only other thing is, with finalizers going away, are you going to get back those finalizer bits? And if so, what will you do with them?
I'm hoping so, Stuart. Yeah, we're going to have to wait for that until we can add more colors.
I suspect this is a dumb question, but it was bugging me the whole time. So in the trick where you do early reclamation of the page that you might still have pointers pointing into, where do you store the forwarding address? Because historically, you would store the forwarding address in the object that you've relocated, but now you've reallocated that memory.
That's an excellent question. It's stored in an off-heap table. That's precisely the point, that we don't want to store it inside of the object, because if we did, we wouldn't be able to do this, because we would, by allocating new objects across this new heap region, we would destroy the forwarding information that allowed it to be sane to do this. So that's why it's stored off heap instead in a hash table.
Another potentially naive question. When you said thread, I kept thinking virtual thread rather than platform thread. Do you have any distinction between those two?
Yes, absolutely. In fact, the distinction is that the optimization only planned for virtual threads and not platform threads. So yeah, it will require using virtual threads to use this, at least the way things are looking now.
Maybe another naive question. So you showed how with certain patterns of color bits you could shift everything down to the right, but what does that gain you? What's the point?
The point is having very efficient store barriers as well. And this was sort of interesting thing. Since we use load barriers, our budget for messing around with barriers and having CPU overheads was quite limited if we wanted to have good performance overall. So we have to have very efficient store barriers as well, and then basically weak referenced reads as well. But yeah, the main thing was doing snapshot at the beginning marking more precisely. When you have snapshot at the beginning marking, you have an object graph, and as you take a snapshot of the object graph, each edge, the first time it's mutated, you need to track that. Most GCs don't have the ability to track which one was the first mutation, but using colored pointers, we can perfectly detect that this was the first mutation of this reference field since marking started. And that means that we can prolong the marking phase. It's quite funny because we're trying to do the opposite of what many other GCs are doing, that we're perfectly fine with the marking phase taking longer and using less threads, whereas traditionally use a lot of threads and use a short amount of time. Comparing to G1, for example, which also uses snapshot at the beginning marking, the performance model sort of relies on that not happening for a very long period of time. Whereas with ZGC, we're sort of expecting that, yeah, well, we'd be doing something concurrently pretty much all of the time. So we need the barriers to be cheap in all GC phases. And these core pointer tricks allow a more spatial optimization technique rather than a temporal one that allows these barriers to be fast in all phases because it recognizes the first storm that doesn't need to do anything after that. Don't know if that makes sense, but yeah. Okay. Yeah.
Sorry if it sounds stupid. I'm not a GC engineer, but if we need to color objects rather than edges, why not to steal some bits from object header and use them instead of pointer bits?
Oh, I think you're asking why not use bits in the object instead of the pointers. And let's see here. Well, first of all, it's slower, so that's one reason. But we also have properties relating to the edge specifically, like the remember set properties, for example. Not a property of the object, is a property of the edge. And since it happens to be that all the other properties we're tracking can be used or can be applied in a slow path using that same fast path check, we can sort of combine the barrier overheads of both marking and remember set maintenance into the same 4-instruction fast path and do everything else in a slow path that's very rarely invoked and also buffered.
Actually, I have a question. So in one of your slides, you're showing how you're going to have a more efficient memory layout. In like the more fragmented slide, you had a bunch of smaller regions, and in the more formatted slide, they were they combined, or was that just? So it's a. But is that a thing where you're going to be combining? Yeah. So like you have a bunch of small regions, and then the other one, are you combining like related small regions?
Yeah, the ranges are combined.
Cool. Thank you.
Thank you.